Chúng ta bắt đầu học ạ. So on the screen is what we studied last week. Last week we begin with the new chapter, new lecture that is about the inner product space, không gian có tích vô hướng. So first of all, we revise what we studied from high school. That is about Euclidean space Rn. I recall that given a vectors in Rn with the coordinate v1 up to vn, the length of the vector usually is denoted by that. That is the square root of v1 square plus v2 square up to vn square. That. And the length now can be called the norm of the vectors. And here we have a four property of the length like that. I just only list it here, and I believe that you know all about that. Then we have the name is a unit vector, that is any vector having the length 1. And the standard unit vectors in Rn is as the following one, the E1, E2 up to En. They are also the standard basis for Rn. And examples for the standard unit vectors in plane is I, like that, and standard unit vectors in R3 are I, J, and K, like that one. So I believe that you know already what is I, J, and I, J, K, because that is in the plane and in space. We know already. And the last line here, that is explain to you something about it. When you compare the length of a vector v and k type of the vector v, the length of c type of v will be absolute value of c multiplied by the length of the vector v, like that. And the next one explain to you what we call the normalizing of the vector v. In case v is non-zero vector and the length has not yet 1, then we can divide the vector v by its length. We get a new vector u, and that vector u is obviously having the length 1, and it has named unit vector in the direction of v. And the process of transform any vector v into a unit vector in the direction of v has named normalization of the vector v. Then we define the distance between two vectors. The distance between two vectors u and v in Rn is defined by that one. And similarly to the length, it has properties like that. So I list it here. And then I recall the notion of dot product. By dot product here, I mean that is tích vô hướng as you study in high school. The dot product of u and v is that number u dot v equals u1 v1 plus u2 v2 up to plus un vn. And the dot product has the following property. We have 5 property. I list it here. Now the Rn, we know already that it is a vector space. Now we give it the dot product or tích vô hướng as we know in high school. Then it will become what we call the Euclidean n space. In Vietnamese, không gian Euclid n chiều. And for that we have the Cauchy-Schwarz inequality. That is some inequalities relating the absolute value of dot product and the length of U and V. And last week, I explained to you in the class why it is a Cauchy inequality. It is quite similar to we know already in high school. It is here. In case U and V are vectors in R2, you get that inequality now became that one, and that one is quite familiar to you. Then after that, we define the angle between two vectors U and V. It is defined by the formula like that. We define it by the cosine of the angle zeta, like here. And we have 5 cases. The first one is here, the second is here. And we pay attention to the middle one. That is the case of the right angle góc vuông. And we have a remark that we cannot define the angle between the zero vector and any other vector. However, if we define two vectors U and V are orthogonal if and only if U dot V equals 0, then usually the vector 0 is considered to be orthogonal to every other vector. And I would like to tell you that the notion of orthogonal is something you know already, and it is very easy for you to imagine. Here is the examples. If you consider the vector U with the coordinate 4, 2 on the plane, so it is the green vector here, then you are required to find all other vectors in the plane so that they are orthogonal to U. Then any other vectors in R2 orthogonal to U will make the red line here. That is any vectors going from the origin to any point on the red line. And you can see that is equation of a straight line y equals minus 2x, or in otherwise, if you consider the vector of the coordinate of any vector inside the plane by v1, v2, then you get that equation. The next two claim, that the first one is about the triangle inequality. Bất đẳng thức tam giác. It is formulated like that, and by geometry you can imagine it is exactly the triangle inequality we know from the elementary geometry. And the equality occurs if and only if the vectors U and V have the same direction. And the last one is a Pythagorean theorem, saying that U and V are orthogonal if and only if we have that equality. That slide explained to you the dot product we have just defined here, or just only we repeat what we studied in high school. You can consider it like multiplication of two matrices. If we write the U and V as a column matrix, then the U dot V equals the product of U transpose and V, and it is here. So that is anything we know in high school already. Now we try to imitate anything for general vector space. Suppose that V is a vector space. Now we define an inner product on V. An inner product on V is a function hàm số. That function will send each pair of vector U and V to a real number denoted by U, V inside the sharp bracket like that one. That is the function sending the pair into a real number denoted by that one. And the function must satisfy the following property here. That is four axioms in definition of inner product. Then, if a vector space together with an inner product will be called an inner product space. And here is an example. The example, obviously, we are going to take the dot product in I. The dot product, I repeat it once again, that is that number. The dot product here. And if I denote it by UV inside the sharp bracket like that, it is exactly an inner product because it satisfies all four axioms. And I would like to tell you a remark. When I write it by dot, here it means a dot product or it is Euclidean inner product for Rn. But when we denote it by UV in between of the sharp bracket like that, it is inner product in general sense for the vector space. Why I say that? That is because in I we have more than Euclidean inner product, we have more than dot product. Here is an example. In R2, here is in R2. If I define a new function by that, U1 V1 plus 2 times of U2 V2, it is again an inner product on R2. And it is not the usual dot product in R2. And I claim to you that any inner product on Rn must be of that form C1 time of U1 V1 plus C time C2 time of U2 V2 up to Cn time of Un Vn, provided that all the coefficients C1, C2, Cn must be positive. And last week I gave you an example in case one of those coefficients Ci to be negative, then the function is not an inner product. It's not inner product. Now, property of inner product to be like that one. So I give it for you to read by yourself. Then whenever we define inner product, we can define the length of a vector U, and that the remark from here, if you take square of both sides, you get square of the length to be that one. And once again, I would like to tell you, in general case, usually we call it the norms of a vector U, not the length. But however, because the word length is quite familiar to us, so I put it here, the norm of U or the length of U. And also we can do anything similar to the Euclidean space. That is, we can define the distance between U and V. We can define the angle between two non-zero vectors U and V like that by define cosine of zeta to be that one. And the orthogonal, that is U and V will be considered orthogonal, denoted by that if and only if the inner product of U and V equals 0. And also we have the process of normalizing a vector. It means that in case the vector V, the non-zero vector V is not yet unit, then we can try to make it into a unit vector in the same direction. And some property of the norms and the property of distance quite similar to the case of Euclidean space. And also we have Cauchy-Schwarz inequality, we have a triangle inequality, and we have a Pythagorean theorem. Nothing new, just only we can follow the formula and we get anything like for Euclidean space. But then the most important thing for inner product, that is the notion of orthogonal. And we know the orthogonal already. And the next, that is the orthogonal projection. Here I explain to you. Suppose that you are given U and V are two vectors in an inner product space V. And suppose that the vector V is non-zero. Then the orthogonal projection of U onto V. The first one, it must be a vector. And I insist by a line here, the underline a vector. That is a vector in V and given by the formula like that. The formula is like that, and that is k time of the vector V. And the number k, I put it in the red frame here. That is a number, and the number defined by the inner product here. In case V is unit vector, then we have that one. So the formula will becomes much simpler like that one. And at this point, I want to insist to you that if you remember from the high school, when you take the orthogonal projection, that the dot line here is orthogonal to the line here. That is why we call it orthogonal projection. And that is described in the property. The vector U minus projection of U on V is always orthogonal to the vector V. And the next one, that is the property of orthogonal projection and the distance. It says that the distance from U to its position on V is always shorter than on other distance from U to any vector V on the straight line containing the V. It is here. By the end of today, we are going to use that property, but I will explain to you later. And then we are going to study the Gram-Schmidt process. As I told you, it is a nightmare for any student, and we are going to study it today. But however, before going to that, we need to know the notion of orthogonal system and autonomous system. A set S of vector in an inner product V will be called an orthogonal set if any pair of vectors inside S are orthogonal to each other. Or by formula, we have that one. If S consists of V1, V2 up to Vn, then we require that the inner product of Vi and Vj equals 0 for any I different from j. And if we require something more, that is any vector inside an orthogonal set to be unit vector, then the set will be called autonomous set. That is, we require not only the below line here, we require that one also. That is, any vector inside here must have the length 1. And in that case, we call the set is autonomous. In Vietnamese is trực chuẩn. Orthogonal is trực giao and autonomous is trực chuẩn. And if more than that, S is a basis, then we have the notion of orthogonal basis and autonomous. Orthogonal basis and autonomous basis, cơ sở trực giao và cơ sở trực chuẩn. I am going to explain to you why we need the notion of the orthogonal basis and autonomous basis. So, at least last week we studied up to this point. So today we begin from here. We continue with some more consideration, more investigation about the orthogonal system. Suppose that S is a set, is an orthogonal set of non-zero vectors. Then S must be linearly independent. Must be linearly independent. You know that? In order to verify something to be linearly independent, we need to consider a system of linear equations, and then we need to show that the system has only deviant solution. And here, in case the system S is orthogonal set, then it is very easy to verify the system we have only deviant solution. Here is some explanation. S is an orthogonal set of non-zero vector, means we have Vi, Vj is the inner product equal 0 for any I different from j. And because non-zero vector, it means that the Vi inner product of Vi is positive orders. Now we consider the equation like that. We need to show that any Ci must be, the equation here has only deviant solution, means on Ci must be 0. How we can do it? This is very easy. You take the inner product of two sides of that with any vector Vi. So on the right hand side, 0, the inner product of 0 and Vi equals 0. And on the left hand side, you get the inner product of that with Vi. Then on the left hand side, you get that one because Vi, Vj equals 0. And then they left only Ci multiplied by Vi and Vi. But because the inner product of that is non-zero, then it implies that the coefficient Ci must be 0. It means that S is a linearly independent. Xin lỗi các bạn, tôi có một cái việc khẩn một tí. So we know that any linearly independent set of vectors which containing no zero vectors must be linearly independent. Then now is a corollary, and that one is very practical for you in doing your exercise. That is it. Suppose that we know already that V has dimension n, and V is inner product square. Then suppose that you are given a system S of n linear n orthogonal vectors. And if we verify that none of vector inside S are 0, then S must be linearly independent. And because of that, S must be a basis for V. Must be a basis for V. Because it is linearly independent, because it is orthogonal set, then it must be linearly independent. And the dimension is n, and the system containing n vectors, so it must be a basis for V. And here is some examples using that property. Now we consider R4, the Euclidean space R4. And we consider 4 vectors V1, V2, V3, V4, like that. And you are required to prove, to show that the set is a basis for R4. Previously, in order to show that the system here is a basis, you need to show two things. The first one, it must be a spanning set. Các bạn phải chứng minh hai điều. The first one is a spanning set, nó là tập sinh. The second one, you need to show that the set is linearly independent. Cái thứ hai là nó phải là độc lập tuyệt tính. But now it is very easy. In case you know what is the inner product, you need only to show that the V1, V2, V3, V4 are orthogonal to each other. Then it is very easy. You need to verify. First, they are non-zero vector, and the inner product or the dot product to be like that. So because of that, you see the system S is orthogonal. And because it is orthogonal, so it must be linearly independent. And the dimension is 4 already. The 4 already, so S is a basis for R4. So if you know that, it's now not so difficult for you to show something to be a basis. Now, that slide show you the importance of an autonomous basis. You know already that given a basis for a vector space, any other vector inside vector space will be given by coordinate. Usually the coordinate is written in the columns like that. But however, you need to find the coordinate of any vector like that. In order to find the coordinate, you need to solve a system of linear equations. But however, in case B is an autonomous basis, it is very, very easy to find the coordinate of any vector. So it is here. Then the coordinate of any vector W relative to the basis B will be like that. So in the next slide, I will show you the formula I prefer to use. Here are some explanation. I give it for you to read it. That using some property about the orthogonal and the autonomous system of B. But now I like to describe it here. In case B is an autonomous basis of the vector space V, and W is any vector inside V, then the coordinate of W relative to the basis B will be like that. In order to find the coordinate of the first coordinate of that, you need only to take the inner product of W and V1. The second coordinate will be the inner product of W and V2, and so on. You can continue it this way. So that formula is what I prefer to use. I like this more than that one. But however, it depends on you. It's up to you. You can choose which one you like. However, that one is somehow is easier to remember. That is the coordinate of any vector will be given by using inner product like that. However, please remember that the formula is true only in the case B is an orthonormal basis. Orthogonal is not yet correct like that. Now, here is some examples. You are required to find the coordinate of that vector. That is some point in R3. That is in space. And you need to find the coordinate of that relative to the following basis. So, first one, they are basis. Second one, they are an orthonormal basis. You can verify it by using the dot product. But however, now here we need to find the coordinate, so it is very easy. The first coordinate to be that, the second coordinate to be that, and the last coordinate to be that, because it is an inner product, and in this case, the inner product is exactly the dot product. We know already, so we multiply them together, we get that one. So we get the coordinate of that vector relative to the basis B to be that one. So I am going to show you some more things about that one. The orthogonal projection. Now in inner product space, we know already if we are given two vectors U and V, two vectors inside the space V, and orthogonal projection of U on V will be given by that. And the most important property of that is that one. U minus projection of U on V is always orthogonal to V. It means that the dashed line here is orthogonal to that one. So we are going to use that to define the orthogonal projection of any vector U onto a subspace here. Suppose that we are given a subspace W of V. Then the orthogonal projection of V onto the subspace W is a vector inside W. I would insist that it must be a vector, and that vector must lie in the subspace W, and that projection will be denoted by that one. And that, by definition, need to verify the property similar to that. That is a V minus projection of V on W must be orthogonal to the subspace V. I put it in the red frame like that. That is definition of the orthogonal projection of V on W. And if you want to consider the picture like that one. Here, W, the subspace, that is something like the plane here. And V is a vector lying here. Then the projection of V onto the subspace W to be that vector. It means the vector going from the origin to that one. And we require that the V minus projection of V on W, that is the red vector going from here to Z. That must be orthogonal to the substrate W here. That is what we require. And that is anything we need to know here. And you can imagine that we are going to use something more here. The blue dashed line here, we are going to use it later, not right now. But however, now we go to Gram-Schmidt process, Gram-Schmidt auto-normalization. So what is a Gram-Schmidt process? It is as follows. Suppose that V is an inner product space. And suppose that you are given any basis B. And Gram-Schmidt process will help you to transform B into an autonomous basis for V. So it consists of so many steps. I will explain to you step by step. The first step, you choose V1 equal U1. That is the first step. It's the easiest step. Then you call W1. That is the substrate of V spanned by the vector V1. Now I go to the second step. Second step, I choose V2. V2 now is no longer U1. V2 is U2 minus projection of U2 onto that one. Or by formula, you get that one. So what you need to remember is that formula. You need to remember. V2 equals that one. But by geometry, it is U2 minus projection of U2 on W1. Then we call W2, that is the substrate of V spanned by V1 and V2. That is the second step. The third step, bước thứ ba. Now V3, we take V3 to be U3 minus projection of U3 onto that substrate. Or by formula, you get that one. With that, you see, you get V2 orthogonal to V1 and VC orthogonal to V2, VC orthogonal to V1. So up to that step, you see we have V1, V2 and VC. Three vectors are orthogonal to each other. Then if we continue this way, you can get Vn to be that one. At any step here, you get V1, V2, V3 up to Vn. And they are orthogonal to each other. That is, if we denote it by B prime, V1, V2, Vn, then it will be an orthogonal basis. It's orthogonal already. But what we need? We need is autonomous basis. So the last step is very easy. We need to normalizing that. That is, we need to divide each vector by its length. So B double prime to be that one. Now that is already an autonomous basis. So here is on what you need to do when you are required to apply Gram-Schmidt to find an autonomous basis for any vector space. So if you look at the slide, you see it is very complicated to remember. But however, if you look at the geometry, it is very natural. Nếu các bạn nhìn vào hình, các bạn sẽ thấy thực chất quá trình này là cái điều rất tự nhiên. So, I'll show you the easiest case here. Now we consider only the plane A2. Suppose that you are given a basis B consists of V1, V2, and suppose that it is not yet an autonomous basis. So it is something like that. Not already orthogonal, not already autonomous. Then you are required to apply the Gram-Schmidt process in the previous slide to find an autonomous basis for R2. So how to do it? You should remember the step here. You can take a look in the slide I up on the border. And then the first step, we take the W1 to be V1. We keep that one. Only the second step, we need to choose W2 to be that one. V2 minus position of V2 onto V1. Then, by that, we get W2 orthogonal to W1. Because here we have only two vectors, that is very easy case. Then we get U1, we get W1, W2 already an orthogonal basis, but now we need to normalizing it, and here we define by the length of that, we get that one is already an autonomous basis for R2. And by geometry, you can see here, V1 and V2 are the green vector here, V1 and V2 is here. And the first step, we take W1 equal V1, so W1 to be that. But now you see, what is the W2? W2 is V2 minus projection of V2 on V1. V2 is here, and projection of V2 onto V1 to be that one. So W2 to be the vector going from here to there. Now I put that vector at the origin, then that vector equals that vector, so W2 to be that one. And obviously W2 and W1 are orthogonal to each other. And the last one, just only normalizing them by dividing by the length, we get that thing. So if you look at the geometry, the Gram-Schmidt is exactly, we take the projection here and nothing more. That, the previous line is the geometry, and now here some applications by formula. Suppose that you are given a basis B consisting of U1, U2, and U3 like that. They are basis for R3, and you are required to apply Gram-Schmidt to find an autonomous basis for R3. So what to do? The first step, we choose V1 to be that. The second step, you take V2 to be that one. And by calculation, you get it here. And the last step, you get that one, V3 to be that. So if we take a look at this line, now because that is a formula by calculation only, I forget any geometry, just only remember the formula. You get that one, V1, you get V1, V2, V3, like that. And I know, I'm sure that V1, V2, V3, they are orthogonal set. And because of that, they are an orthogonal basis for R3. And the last step, we need to normalizing them. Normalizing them. I'm sorry. So by that we get an orthogonal basis like that one, and we divide it by the length, we get an orthogonal basis for that. So that is a calculation according to the Gram-Schmidt process here. Now you have another examples, just a little more complicated. Suppose that you are given a homogeneous system of linear equation like that, and you know already all the solution of the system we make a subspace of R4. Now you are required to find an autonomous basis for solution space of that system. We know already how to find the dimension, how to find a basis for solution space. So now, first you need to find a basis for solution space, and then you need to apply the Gram-Schmidt to find an autonomous basis for that. Here it is. In order to solve it, you get it here. Using Gauss-Jordan elimination, you make it to be that one. Then, because of that, once again I call your attention to the columns containing the leading one, that. So it means that the third variable and the fourth variable are free. Free means that we can give it any value s and t. Then the solution will be that one. And if you write it in the form s times of that one plus t times of that one, then you see that vector and that vector will make a basis for the solution space. So please remember that column vector and that column vector will make a basis for the solution space. That is here. So we get the basis already, and now we need to make to use Gram-Schmidt apply to that one to get an autonomous basis for solution space. Fortunately, the basis consists of only two vectors. So it is very easy. We need only to apply one set, two set. The first set we take that one. Second set V2 to be that one. So we get V1 and V2. They are already orthogonal basis. It is already orthogonal basis. We normalize it and we get that one. That is autonomous basis. Now you can verify it. And the last will be the least square analysis or in Vietnamese. The least square in Vietnamese, bình phương tối thiểu. We are going to study it after the break, so we have the break now. So we continue, but before continue, I want to tell some things in Vietnamese. Giờ nghỉ có mấy bạn lên đây hỏi tôi, và tôi nghĩ rằng là nếu mà hỏi như sau thì rất nguy hiểm. Bạn hỏi là tại vì cái kiến thức này nó sẽ nằm ở trong phần chúng ta sắp sửa thi, và tôi đã giải thích ở trên lớp rất nhiều lần rồi. Bạn hỏi spend là cái gì ạ? Các bạn còn nhớ cái spend là cái gì không ạ? Thôi câu hỏi dễ hơn ạ. Tôi cho một vector như thế này khác không? Cứ cho nó chĩa thẳng lên rời. Vậy cái spend của nó là cái gì? Spend của nó là cái gì các bạn nói đi ạ? Ok, đúng rồi, bạn cứ vung tay thoải mái đi ạ, không cần phải nói ra miệng nữa. Spend của nó. Vậy nếu một cái vector mà nó như thế này thì spend của nó là cái gì ạ? Ok, một vector spend là cái đường thẳng chứa vector đấy. Hai vector là cái gì ạ? Spend của nó là cái gì ạ? Hai vector cái spend là một mặt phẳng chứa trong nó. Câu hỏi còn quan trọng hơn, câu hỏi này không phải quan trọng hơn nhưng nó bản chất hơn. Mặc dù cái này các bạn biết từ phổ thông rồi, mặc dù ở trên lớp đã từng giảng cái điều đấy, nó ở dòng cuối cùng của cái slide nào đấy. Khi nào thì hai vector song song với nhau? Ở phổ thông nha, các bạn cứ nhớ đi ạ. Hai vector là song song với nhau khi và chỉ khi thằng này bằng k lần thằng kia, đúng không ạ? Bằng một số bội lần của thằng kia. Hai vector ở trong được coi là bằng nhau nếu như chúng ta đặt vào gốc là nó cùng như nhau. Nhớ hộ tôi điều đấy. Vì thế các bạn hãy nhớ hộ tôi một điều. Hai vector như thế này, nếu tôi có hai vector như thế này thì không thể nào một thằng này bằng k lần thằng kia, đúng không ạ? Nó chỉ có thể bằng k lần thằng kia nếu chúng cùng phương với nhau. Như thế này đã là khác phương rồi, hai thằng nằm này là khác phương rồi. Cái đấy chúng ta phải học từ phổ thông chứ không phải ở trong giáo trình này. Giáo trình này chỉ hệ thống lại những điều đấy thôi. Bạn nữ phía dưới bắt đầu học tiếp đây ạ, không phải quay lại đằng sau nữa đâu ạ. So now we go to the least square analysis. That is bình phương tối thiểu. Now the first one we need to define what is it? Orthogonal subspace. Here by formula, suppose that we are given two subspaces W1, W2 in an inner product space V, and we say that W1, W2 are orthogonal to each other if we choose V1, V2, any V1 in W1, any V2 in W2, they must be orthogonal to each other. By definition, it is something like that. But once again, that you know already in high school. Now, the first one here, in case V is the plane R2, you get W1 to be that and W2 to be Z1. Please remember that the subspace of the plane must be a straight line going through the origin. And we have W1 and W2 now are two blue lines here. And they are orthogonal to each other because if you take any vector lying in here and any vector lying on there, they must be orthogonal to each other. Now I make it just a little more complicated by consider the space here. In the space, you consider W1 to be the plane here and W2 to be the straight line containing the red vector here. And once again, they are orthogonal to each other because if you take any vector lying on the plane and any vector lying on the straight line, they are always orthogonal to each other. So the imagination, the illustration you have already in the high school, but now we define it by this one. And here as the case, the two subspaces are orthogonal to each other. And I require you to help me to verify the following. If you consider the space and you consider the plane x, o, y and x, o, z. Nếu các bạn xét không gian 3 chiều, các bạn xét hai cái mặt phẳng tọa độ là x, o, y và x, o, z. Both of them are subspaces of R3, but they are not orthogonal to each other. Please help me to show that. Please help me to show that. Okay, next. Now we have already the notion of orthogonal subspaces, and here is some kind of homework. If you like, you can write it. Suppose that you are given W1 is a subspace spanned by two vectors like that, and W2 is a subspace spanned by one vector like that. And you are required to verify the two subspaces are orthogonal to each other. And the hint for you, gợi ý cho các bạn, because we have that one. So that is your homework, you can try it. The next one, I help you to define orthogonal complement of W. Suppose that W to be a subspace of V. V is the inner product space. Then a vector in U will be set orthogonal to W if U is orthogonal to every vector inside W. That is quite similar to the case when we define two subspaces orthogonal to each other. Then the next one, the set of all vectors inside V which are orthogonal to any vector inside W will be called orthogonal complement of W. In Vietnamese we call it phần bù trực giao. Orthogonal complement of W. Phần bù trực giao. Then it will be denoted by that W perpendicular. That notation has name perpendicular. That is a set of all vector V, so that the inner product of V and W equal 0 for any vector W inside the subspace WK. And that one is an example you can verify. Then the orthogonal complement of 0 vector must be the V, the whole vector V, and the orthogonal complement of V will be 0 substrate. So that is the notion of orthogonal complement. And if you going back to the picture here, it is very easy to imagine that the orthogonal complement of that blue line will be the other blue line. And in that case, the orthogonal complement of the plane will be that line. And the orthogonal complement of that line will be the plane here. So that is a notion of orthogonal complement. But however, in order to imagine, you should take the example from the geometry. And that is something very useful for you to imagine the new notion here. Now here is a remark. Suppose that W is a subspace of V, then the first one is orthogonal and complement must be a subspace. It must be a subspace. The second one, the intersection of W and its complement will be zero only. Một không gian con và phần bù trực giao nó chỉ giao nhau ở vector không. In the geometry, in the picture I draw for you, you can see it. And now, if you take orthogonal and complement and you take orthogonal and complement once again, you will going back W. It means that one W and its orthogonal and complement orthogonal and complement of each other. And here is some example for you to see. Now, in case that is easier than the picture I show you in previous slide. Now, if you consider the R2 and we consider the Hamilton Ace to be the W, that is substrate, then its orthogonal complement will be the OY exists here. And if we consider V to be that, then you see W to be here and W perpendicular to be here, and you see. Then complement, orthogonal complement will be the Y axis. It is again a subspace of R2, and the intersection of W and W perpendicular to be the origin only. And if you take that again, orthogonal complement, once again you get back the W. So that example help you to verify that one. And my question for all of you is the following. If you consider R3 like that, and you consider W to be the OX, then what is it? Orthogonal complement of OX? Yes, that is a plane. That is a plane YOZ. And then once again, then you can verify the property 1, 2, and 3 by that thing. So that is what we can imagine from the geometry we study already in the high school. And from that property 1, 2, and 3, we get a new notion has named direct sum in Vietnamese tổng trực tiếp. It's following. Suppose that W1, W2 are two subspaces of Euclidean space Rn. Like that. Now, if each vector x of Rn can be written uniquely as a sum of a vector W1 in here and W2 in there, Z. That is x equal W1 plus W2 Z. Then we say Rn is direct sum of W1 and W2, and by notation we get that Rn equal W1 direct sum with W2, and the notation here is pronounced like O plus is factor O, that is the letter like that, so they call it O plus, that is direct sum. So that is the notion of direct sum, and to understand direct sum, once again please look back at the orthogonal complement, and once again look back at the geometry examples I draw in the slide. So here are some property of orthogonal subspace. Once again we go to the orthogonal notion. Suppose that W be a subspace of I, then we have the following property. The first one, the dimension of W plus dimension of its orthogonal complement equal n. That's the first thing. Second thing, that is Rn equals direction of W and its orthogonal complement. And the last one, I put it here, but we say about it already in the previous slide. So we have a C property for orthogonal subspaces. So you need to remember the number 1 and number 2. That one, once again, we're going back to the orthonormal basis for an inner product space that concerning the orthogonal position, and that once again concerning the Gram-Schmidt process. Because during the break, some of you are going to ask me what is the formula for the position of a vector V onto a subspace, and here it is your formula. Suppose that the W, the subspace W of V, will have an orthonormal basis consisting of U1, U2 up to UP. Then position of any vector V on W will be given by that one. The formula is here. And if you remember, if you take a look back to the Gram-Schmidt process, you will find the position of V on W in case U1, U2, UT is not an orthonormal basis. Then in that case, the coefficient here must be just a little more complicated. I will not repeat it here, and I tell you only in case the basis is an orthonormal basis, then the formula is very simple like that, very easy to remember. And here is some explanation. I will skip it. Here are examples. If you are required to find projection onto a subspace, how you can do it? Suppose that you are given W1, W2 like that, and V to be that one. And you need to find the projection of the vector V onto subspace W. And W is spanned by W1 and W2. So what you need to do? The first one, you need to see that if you multiply, if you take the dot product of W1, W2, they are orthogonal vector. It means that W1, W2 is an orthogonal basis for W. Then, the first step here, we need normalizing that by dividing each vector by its length. So we get an orthonormal basis for W to be here. Now, in order to find the position of V onto that space, we apply what we have already in the previous slide. It is here. Then position of V on W now equals the inner product of V and U1 plus V U2 U2, and it is here. So if you remember that, it is very easy to find. So once again, you see the first two lines in the solution here, that is exactly the Gram-Schmidt process. Fortunately, in this case, two vectors are orthogonal to each other already. So we need only to define each vector by its length and nothing more. Now, again, show you here. That one. That picture we have already in the previous slide. That is V to be here and the is orthogonal projection on the substrate W to be that point. And if you look at the dashed line here, the length from V to its projection is shorter than any other length from V to W. And it is described in that inequality. The distance from V to its projection is less than the distance from V to any vector V lying on the W here. And it is explained in that property. And here is a formula, and the geometry or what easier for you to remember is that one. So I want to show you this first, and then we go to that things. And everything is explained here. And it will be explained by using Pythagorean theorems, and you can read it in the slide on the Moodle. So by what we can say that on the vector among all the vector in the substrate W, the vector V, the position of V on W is a vector closest to V. Closest to V. We are going to use that in the next things. But before going to the square, to the least square problems, we need to once again to consider the substrate, fundamental substrate of a matrix. Suppose that we are given a matrix A of psi m by n. I recall to you that we have the column space, row space, null space, and left null space here. They are subspace of Rn corresponding like that. Then I claim that those subspaces are orthogonal complement of each other as follows. Here, if you consider the column space and you take its orthogonal complement, you will get left null space. And once again, if you take null space of here, that is a null space of R transpose, or it is a left null space, and its orthogonal complement is column space. And here, if we take row space of A or column space of A transpose, and its orthogonal complement will be null space of A, or null space of A will have orthogonal complement to be the row space of A. Next, because we know already W plus W and direction which is orthogonal complement will be Rm. So here we get the column space of A O plus with the left null space of A will be Rm because they are subspace inside Rm. And here also we have that thing. And the other way, if we consider those substrate lying inside Rn, you get the row space of A O plus with null space of A will be Rn. And here. So we have four things at this four things about orthogonal complement corresponding to the fundamental substrate of a matrix. I insist to only one thing, and from here you can imply all the others formula. And examples about that is the following one. Suppose that you are given a matrix A. the first one, you need to find the four fundamental substrate of that. Then that is already in the reduced row echelon form. So anything is very easy for you. The column space will be spanned by the first column and the last column. And the row space will be spanned by the first row and second row. And then the null space will be here. Because if you solve it, you get only one solution here. Then 80 to be that, and if you use Gauss-Jordan elimination, you reduce it into that one, and to solve it, you get that will be free variable. By free variable, you can give it any value s and t, and here the left null space will be spanned by that vector. So with that, we find all four fundamental subspace, and then we can verify that the column space by here, column space here, row space is there, and null space here, and left null space to be here. Then you can verify that orthogonal complement of column space of A will be that one, and that things that I will leave it for you to verify during your exercise. Now, just a little more concrete. If you consider W to be spanned by two vectors like that, you need to find a basis for W and find a basis for the orthogonal complement of W. How to do it? The first one to be here, and if you apply the Gauss-Jordan elimination to transform it into that is already in the reduced row echelon form. And because of that, the column space will be spanned by two things here, and those vectors are linearly independent, so there is a basis for that. It is a basis for the column space, and the orthogonal complement of that will be left null space. And you can find it here, and it will have that is a basis for the column space for orthogonal complement of W. So here you should remember once again that will have dimension 2, and that will have dimension 2, and you can verify that the dimension of W plus dimension of W perpendicular equals 4. And once again, you can verify WO plus W's perpendicular will be 4. That is a direct sum. Now I go to the least square problem. The least square problem leads to solving a system of linear equation. Now suppose that you are given a system of linear equation like that, Ax equals b. If fortunately the system is consistent, when the system is consistent, we can use Gaussian elimination or Gauss-Jordan elimination to solve it. We can find the solution, the exact solution. But in the case when the system is inconsistent, it means that the system has no solution. What do you want to do? We want to find the best possible solution to the system. That is, we need to find the value of x so that the difference between AX and B is as small as possible. Trong trường hợp mà cái hệ phương trình này không có nghiệm thì chúng ta muốn tìm cái nghiệm tốt nhất có thể được. Thế nào là tốt nhất? Nghiệm tốt nhất có thể được đấy là cái nghiệm x sao cho cái khoảng cách từ cái AX và cái B này, khoảng cách giữa AX và B là nhỏ nhất có thể được. Vì hệ là không có nghiệm cho nên cái khoảng cách không bao giờ bằng 0, nhưng nhỏ nhất có thể được. Đấy là cái mà chúng ta muốn làm. So we are going to do as follows. Here, suppose that AX equal B, that is a system of m linear equation in n unknowns. So we need to find a vector I denoted by x hat, that is a vector inside Rn, so that the length or the distance between AX and B is smaller, as small as possible, or we need to find the x hat so that it minimizes the value here. So we need to know what is the AX minus B. If we can find x hat satisfying that, we call it least square solution of AX equal B. Nếu tìm được, khi nào tìm được một cái thằng x mũ như vậy, ta sẽ gọi nó là nghiệm bình phương tối thiểu, least square of AX equal B. Now I analyze it. A to be a matrix of sign m by n. X to be any vector inside n, that is a column vector. AX, if we multiply AX here, we always get some vector inside the column space of A. I leave it for you to verify. A multiplied by x will be a vector lying in the column space of A. Now, because the system is inconsistent, means B does not belong to the column space of A. Hệ này là hệ không có nghiệm, có nghĩa là B không nằm trong không gian cột của mặt trận A. Cái đấy chúng ta biết từ hôm trước rồi. Because A equal B is inconsistent, B does not belong to the column space of A. Then we need to find a vector x hat in Rn so that AX hat is closest to B. Now I summarize it here. Suppose that here we need to find the least square of that. That is to find an exact. Okay, I show it here. Now, if I choose AX hat to be the position of B on the column space of A, remember that B does not belong to column space of A, so it means B staying outside of column space of A. Now we project it orthogonally, project on column space of A, and we call AX hat to be that one. Then you will get that thing. And in that case, obviously, the AX hat will be closest to the vector B. And because of that, you see B minus X hat must be orthogonal to the column space of A. Or if we multiply them together, we get A transpose multiplied by B minus AX hat equals 0. Or you get that one. But if you look at that equation, the last one, on the right hand side, that is anything we know. We know A already, we know B already. So A transpose multiplied by B, we know already. And on here, A we know already, A, T we know already. So X hat, if we choose X hat to be like that, then X hat must satisfy the system of linear equation like that. And that it has named the normal system associated with Ax equal B. So I summarize it by saying, in order to find the least square solution of that, it means that we need to find x hat satisfying that one. And that system, we know exactly that the system is consistent. We can always find x hat satisfying that one. So that is a summary of things. Để giải bình phương tối thiểu một hệ phương trình không có nghiệm, thì thay vì cái hệ ax bằng b, chúng ta sẽ xét cái hệ này. Hệ này chắc chắn có nghiệm, và cái nghiệm của hệ này chính là nghiệm bình phương tối thiểu mà chúng ta cần tìm của cái hệ ax bằng b. Here are examples, a very easy example. Suppose that we are given a system Ax equal b, with A to be that, x to be z1, and b to be z1. And we know that the system is inconsistent, and we need to find the least square solution of that. So we follow the previous slide. First we need to find A transpose multiplied by A, and then A transpose multiplied by B. Then the associated normal system to be that one. Now our least square solution will be a solution of that system of linear equation. And solving that, we get x hat to be that one. That is solution of that. So that is exactly the least square solution of Ax equal b. And once again, now the orthogonal projection of b on the column space of A to be A multiplied by the x hat. So we get that the projection of b on the column space of A to be that one. So by that calculation, you can just only one calculation, you get two things. The first one, you can find the least square solution. The second one, you can find the orthogonal projection of B on the column space of A. So that is on what we study. That on what we need to know about inner product space. And we continue with the chapter number 6 here. The chapter number 6 is named a linear transformation of infinity các phép biến đổi biến tính. So we begin the first one. Suppose that we are given two vector space. Now we forget for the moment. We forget the inner product space. We just only consider vector space or linear space. Suppose that V and W, they are two vector space, and T is a map. So let me ask you, have you know what is a map? Các bạn làm ơn cho tôi hỏi, ngày xưa tôi học phổ thông không giống các bạn. Ánh xạ các bạn đã học là cái gì chưa? Tập hợp là cái gì chưa học gì ạ? Tập hợp thì học rồi, ánh xạ chưa học thì ok. So we first by mapping. Sorry, chắc là chúng ta phải sang tuần sau. Tôi nhìn nhầm, tôi cứ nghĩ là mới có 11:15. Sorry các bạn, tuần sau chúng ta bắt đầu chỗ này à?